Hello everyone, welcome to this week's Mathcast podcast. Today we are joined by an academic scholar and a Math Leap student. Today we are joined to discuss the Goldbach Conjecture and other fascinating prime topics, such as the Mersenne Primes, twin prime conjecture, and highly composite numbers. Without further ado, let's get started. Alright, so why was the Goldbach Conjecture called this way?
Well, it was called the Goldbach Conjecture because it was devised by the genius Christian Goldbach. He was born on the 18th of March in 1690 in the Duchy of Prussia's capital, Königsberg, which today is known as Kaliningrad in Russia. His father was a Protestant church minister. Euler's father, Paul Euler, was a Protestant church minister as well, in Basel, Switzerland, when Euler was born 17 years later, which is quite a cool fact, seeing as the relationship between Goldbach and Euler was very strong. Goldbach went on a long voyage from 1710 until 1724 after graduating from the Royal Albertus University. There, he learnt maths at Oxford University in England from Isaac Newton, and subsequently got hired as a math professor at the St. Petersburg Academy of Science back in Prussia. He met Euler, and they became close friends. Goldbach convinced Euler to pursue maths instead of medicine, so without him we might not have all the maths Euler gave to the world. Goldbach was a credited mathematician in his own right though. He was so good the Tsar, Peter II, wanted him to tutor him. Goldbach had to move to the capital, Moscow, and after Peter died, decided to stay there because he had a more financially stable job in the Russian Ministry of Foreign Affairs.
He and Euler, though, continued to write each other letters, and it was in one of these letters that Goldbach devised the Goldbach Conjecture. And Euler helped him refine it to the conjecture we know it today, and he made it more concise and understandable. The conjecture states that every natural number, which is a whole positive number, over 2 is the sum of two primes.
So the first even natural number over 2 is 4. So can you think of two primes that add up to make 4?
2 and 2.
For 6 it would be 3 and 3, for 8 it would be 3 and 5, for 10, 5 and 5, 12, 5 and 7, 14, 7 and 7. I could go on all day. It sounds like we've proved this conjecture. It seems pretty obvious. But we're talking about every even natural number in existence.
That's not just 100 million. No, that is every single number up to infinity, which is quite frustrating in math, that how you just can't just try it out and then see if it works. But you have to actually rigorously prove this conjecture and generalize it for every single number up to infinity.
We have, however, through loads of number crunching and very powerful computers, proved the conjecture from all numbers from 4 up to the number which is so long, 4 times 10 to the power of 18. I can't even comprehend that number. But until we have a generalized proof that proves that above 4 times 10 to the power of 18, it still works, mathematicians just can't accept it as solved. Primes are tricky like this. There are so many unsolved prime conjectures.
So another example of some prime conjectures is the twin prime conjecture, and it has been around for an extremely long amount of time, and it's still unsolved. So what the twin prime conjecture is it's twins, so they're very close primes, namely a difference of 2. So for example, 11 and 13, 5 and 7, and this list goes on for a really long amount of time, and it's mathematicians think that the twin prime conjecture is true, that these sets of primes go on forever. But like Rhea said, until we have a generalized proof, we can't fully accept this, and we can't fully say that it's true.
But how do we find all these prime numbers to conjecture with? One way of doing this is to use the Mersenne Prime method. We use the form 2 to the power of n subtract 1. Sometimes this doesn't work. For example, 2 to the power of 4 subtract 1 is 15, and that's not a prime number. But the largest prime number in existence was found using the Mersenne method, and it's a very accurate way to predict some really large primes. What about the opposite of primes?
So there are numbers called highly composite numbers, opposite of primes, and an example of this is 1, surprisingly, is that 1 isn't even a prime number. How can this be? So highly composite numbers are numbers which have more factors than any number before it. So 1 is apparently a highly composite number, even though it's not a prime nor a composite number. It just has its own category. 2 is a highly composite number because it has more factors than 1, namely 2 and 1. 4 is a highly composite number because it has 3 factors, 2, 1, and 4. 6, 12, and this list goes on. This list goes on. There are fewer highly composite numbers the more you go on. Alright, so like I said in the highly composite numbers section, 1 isn't even a prime number. And why is this? Well, this is because of the fundamental law of arithmetic. It sounds very important because it's a fundamental and it's a law, right? So it states that every integer greater than 1 is either a prime number or it can be expressed in the form of primes. So an example of this is, for example, 15, right? For example, 15 can be expressed as 3 times 5, right? The two prime numbers multiplied together gets 15, right? This is a unique set, and unique isn't just used as a fancy adjective. No, well, it has a meaning, right? Unique because, for example, other than 3 times 5 or 5 times 3, you can't find another prime combination that gives you that product of 15. Well, 1 breaks this.
Because we can just put times 1 in the end infinitely amount of times. 15 can equal 3 times 5, 3 times 5 times 1, 3 times 5 times 1 times 1, 3 times 5 times 1 times 1 times 1. I could go on forever. This makes the composition not unique, and it breaks the fundamental law of arithmetic. Also, 1 only has one factor. 1. That might fit the 1 and itself rule that we're taught in primary school, but the actual definition of primes is that they have 2 factors.
1 and itself, not just 1. And for a long time, mathematicians actually had 1 as being a prime number, but it broke the fundamental law of arithmetic, and in which they had to remove it. Thank you so much for listening, and we hope you enjoyed.